Radioactive decay. So radioactive atoms are like sinking ships. They throw stuff out to get balance. Radioactive decay is totally random. There's nothing you can do to speed it up, and there's nothing you can do to slow it down. There are three main things a nucleus can throw away: alpha particles, beta particles, and gamma radiation. If you plot the mass number of a nucleus, so that's the nucleon number, the number of protons and neutrons added together on the y-axis, and on the x-axis you plot the number of protons, so the charge of a nucleus, then you get a line called the line of stability. If a nucleus, an atom, is above that line, it wants to get back down towards the line, and if it's below that line, it wants to get up to that line. So that line's where it wants to be. If it's above the line, say for instance, because it's got too many neutrons, then it's not got enough charge. So it undergoes beta minus decay. A neutron turns into a proton and it moves closer to the line. If it's below the line, say it's got too many protons, that will undergo beta plus decay. So it'll create a neutron and it'll move up towards the line. If it's just too heavy altogether, then it'll get rid of some mass via alpha decay and move closer towards the line. You need to be able to sketch this graph for A-level physics and explain it. So, alpha decay. The unstable nucleus has got too much mass. It kicks out an alpha particle. So an alpha particle is a helium nucleus. It's got 2 protons and 2 neutrons. It leaves behind a more stable element with a mass number down by 4 and an atomic number down by 2. So for instance, that's the general equation for an alpha decay. We can see that we have to conserve mass, so the numbers on the left-hand side at the top have to equal the sum of the numbers at the top on the right-hand side, and the same for charge. The numbers along the bottom have to be equal on the left-hand side and the right-hand side. So there's an example of alpha decay. If we're conserving mass, we can see that 213 is 209 plus 4, and at the bottom we're conserving charge. 85 equals 83 plus 2. In beta minus decay, you've got too many neutrons. So a neutron will turn into a proton and then, in order to conserve charge, kick out an electron. So it kicks out an electron, which is called a beta particle or a beta minus particle. So the mass number stays the same, but the atomic number goes up by 1 because we've got 1 new proton. Note that the atom doesn't lose an electron from its shell. It's from inside the nucleus. It creates a brand new electron and then it kicks that out. So in general, the equation for beta minus decay is like this. The atomic number, the mass number will go up by 1. The mass number will stay the same, and the number of protons will go up by 1 because it's kicked out an electron. It'll also kick out an antineutrino of electron flavour. So there's an example. So 42 is 42 plus 0 plus 0, and on the bottom 19 is 20 minus 1. In gamma decay, the unstable nucleus has too much energy, so it kicks out a gamma ray photon. The gamma ray has 0 mass and 0 charge, so the mass number stays the same and the atomic number stays the same. So in general, we write down the equation for any element undergoing gamma decay as that. Notice that gamma decay is the only type of radioactive decay that doesn't change the element that you've got. Any other radioactive decay changes the element that you have. So in every decay, energy, charge, momentum, baryon number and lepton number must be conserved. And we can represent the decay by an energy level diagram for the nucleus. So each flat line represents an energy state that the nucleus is in. And we draw arrows between them to show how the energy of the nucleus is changing. So for instance, we can start with lead, and it can decay via alpha emission, so the energy of the nucleus will go down, and it will be in an excited state, and then it'll further decay by emitting a gamma ray photon to get rid of the excess energy to go to the ground state. Or it could just emit alpha emission and go straight to the ground state. So nuclear decays can happen in multiple stages. So ionisation is when radiation knocks out the shell, a shell electron from another atom. So for instance, here's an alpha particle, it interacts with another atom, it gives some energy to one of its shell electrons, and that electron escapes completely. So now we have an ion because it's lost an electron. So it's got one more positive charge in this case than it has negative charges. Ions are dangerous because they can damage DNA. So that's the mechanism by which radiation can cause damage to humans, not directly, but indirectly through creating ions. Alpha radiation is the most ionising, beta radiation is medium ionising, and gamma radiation is the least ionising. That means that the more ionising something is, the more it reacts with matter, it gets stopped easier, so it has a shorter penetration depth. So alpha particles will be stopped by paper and typically only travel a few centimetres. Beta particles need to be stopped by aluminium and they'll travel a longer distance, maybe 10 centimetres to 15 centimetres. And gamma rays will travel a much longer distance and be stopped by lead. So, the risks and uses of radiation. So, radiation can ionise atoms. So, in an atom, the number of protons equals the number of electrons, but if an atom can lose or gain an electron, then we call it an ion. So, ions with too few electrons are positive, and ions with too many electrons are negative. So, once an atom and a cell are ionised, they can damage DNA. So, a high radiation dose can kill cells completely. A low radiation dose can damage the DNA and cause mutations that lead to cancer. We can also use radiation to help us with medical treatments. So if we want to see how a fluid flows around the body, we can give a small amount of radiation that goes into someone's bloodstream and it's carried along by the fluid inside their body. Then by detecting where the radiation is, we can see where the fluid is, detect blockages and things like that. Notice for this kind of detection, you're going to have to use something that creates gamma radiation, so it can travel from the inside of someone's body to the outside of their body without doing them any damage. If someone ingested alpha radiation couldn't leave their body, it'd be trapped inside, and because it's the most ionising, it would do the most damage inside the person. We can also use radiotherapy to kill cancer. So we can fire gamma rays at cells, and if we give them a high enough dose, we can then kill those cancer cells. Other uses for radiation include finding leaks in underground pipes. So you can introduce a radioactive tracer into the fluid, and again, if it starts to pool at a particular point because there's a leak, you'll detect more gamma radiation from that point on the ground, and you can tell that an underground pipe has a leak. We can also use smoke detectors that use alpha radiation to detect smoke particles. So irradiation and contamination. Irradiation is when an object near a radioactive source gets exposed to radiation. Irradiation doesn't make something radioactive. Contamination is when you get radioactive atoms on you. So that means that you're carrying around radioactive dust and you've become radioactive. So you can reduce your exposure to radiation by using lead shields or remote-controlled robot arms in a nuclear power plant and things like that. Now, as well as the radiation that you might get from a particular source, there's just a general amount of background radiation around us. And the radiation dose is the amount of radiation you've been exposed to. We can measure the radiation dose in sieverts, SV, and it's often measured in millisieverts. So that's 1,000th of a sievert. So the becquerel, right, that's the amount of radioactive activity, and the sievert is the amount of radiation that someone's been exposed to. There's radiation around us from the background radiation from cosmic ray showers and from radioactive rocks. There are also man-made sources of radiation, for instance, nuclear power plants that create nuclear waste, or nuclear accidents like Chernobyl that seed the atmosphere with radioactive elements. So if you look at the sources of background radiation, you can see that 50% of the radon gas is released by rocks such as granite, and only about 10% of the background radiation comes from cosmic rays. So background radiation is relatively speaking very small, and the amount that you get depends on where you are, your location, and what you do, your occupation. So if you live in a place like Aberdeen, for instance, where there's a lot of granite rock, that'll give off a lot of radioactive radon gas, and so you'll get more background radiation. If you live at high altitude, you'll get less protection from the atmosphere from cosmic rays, and you'll get more radiation. Now, if you work in an occupation like at a nuclear power plant, or in the medical profession as a radiographer or something like that, you'll be close to sources, artificial sources of radiation, and they'll increase your exposure. The power and intensity of radiation, it follows the same equations as any other power and intensity factors in physics. So the power output is going to be the energy divided by the time, and the intensity is going to be the power divided by the area. So if we imagine a cross-sectional area and ask how much radiation is crossing it per second, that will be the power going through that area divided by the area. So if we've got a radioactive source, that is going to radiate in 3 dimensions. So you can imagine the surface of a sphere outside the radioactive source, where the surface area of that sphere is increasing with distance as you move away from the source. So the intensity of a radioactive source is going to be a constant K divided by R squared, where R is the distance you are from the radioactive source. So if you move twice as far away from the source, the intensity you feel will go down by a factor of 4. Now this equation only applies to gamma radiation. It's not going to apply to alpha radiation and beta radiation because they travel such short distances anyway that if you move further away from them, you just won't detect any radiation from them. But gamma radiation is electromagnetic radiation, and that's spread out just like a light wave would or a sound wave would. So the intensity is going down as 4 pi r squared, where that's the surface area of the sphere that the radiation is being spread out over. So as I said, the intensity is an inverse square law. In principle, it only applies to gamma radiation. The gamma radiation is going to spread equally in every direction because it isn't absorbed, but beta and alpha radiation are absorbed, so you just won't see this effect.